Section 7.2, we're going to look at sampling distributions specifically for proportions. Okay, so what we're talking about here is the sampling distribution of the sample proportion. In other words, if I took all of the samples of a particular size that I could out of a population and I calculated some proportion for each of them, and then plotted them all. That is what we're talking about here. And the goal is for you to be able to know and describe the shape, center, and variability of these sampling distributions. Okay, so as examples, we have 6 of them here, and they are talking about like take the sample proportion of orange candies. So like in the Reese Pieces, what proportion of the sample is orange. Okay, and they have different population proportions. So both of these 10% are orange, both of these 50%, and then both of these 90%. And then pay attention to the sample size as well. The 3 on the top are taking samples of 25, and the 3 on the bottom are taking samples of 100. Right, so when we talk about shape, anytime we're dealing with a smaller sample size, if P is close to 0, so the population proportion, if that is close to 0, the distribution will be skewed to the right, okay, because most of the values will be here, and then we'll have the long tail out to the right. So then the opposite would be true. If P is close to 1, then it's going to be skewed to the left. Okay, when P is close to 0.5 or when the sample size gets bigger, all right, then the distribution becomes more symmetric or normal. All right, that was for shape. For center, the mean of the sampling distribution is equal to the population proportion, okay, because P hat, that sampling distribution or sample proportion, is an unbiased estimator. So whatever the proportion is for the population, that is also the mean of our sampling distribution. All right, then when we talk about variability, there's 2 things we got to look at. We got to look at both N, our sample size, and P, the population proportion. So all with the sample size being equal, okay, anything where P is closer to 0.5 is going to have larger variability. All right, anything where P is close to 0 or 1 is going to be smaller variability. So when P was 0.5, the standard deviation was 0.1. When P is 0.1, the standard deviation is 0.060. So it gets smaller when the population proportion, when P is closer to 0 or 1. Okay, so not only does P affect the variability or the standard deviation, so does N. All right, so as our sample size gets larger, our standard deviation gets smaller. And if we think about that, it makes sense because generally in statistics, if I have a larger sample size, I'm going to be more accurate, which means my standard deviation would get smaller because my numbers are going to be closer together because they're all more accurate. Okay, very specifically, the amount that it shrinks is if I multiply the sample size by 4, it cuts my standard deviation in half. All right, so we have an example of that here. Here, N is 25, and the standard deviation was 0.060. All right, if I multiply that sample size by 4 and take samples of 100, it cuts my standard deviation in half from 0.06 to 0.03. And we'll look at why when we get to the formula for standard deviation here in just a second. All right, so to sort of sum it up here on one page, when we talk about center of the sampling distribution of a sample proportion, okay, the mean is equal to the population proportion. When we talk about standard deviation, here is the formula. P times 1 minus P over N, and then we take the square root of that whole thing, as long as the 10% condition is satisfied. Okay, so remember we talked about this last chapter. A 10% condition just says your samples have to be less than 10% of the whole population. All right, that way we're okay with sampling without replacement. All right, and then when we talk about shape, we can say that the sampling distribution of p hat is approximately normal, which means we can use our normal probabilities, so like normal CDF and all of those things, as long as the large counts condition is satisfied. Okay, here's what the large counts condition says. N times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. Okay, so the number of successes in our sample and the number of failures in our sample has to be greater than or equal to 10 for both of them. As long as that is true, then we can say that the sampling distribution is approximately normal. So if we go through an example, we have 84% of students at a large high school regularly use a backpack. We're going to take a simple random sample of 100 students and find p hat, the proportion of students in our sample who use a backpack. All right. So first thing we want to know is what's the mean of the sampling distribution of p hat? Well, the mean is equal to the population proportion, which is 84% or 0.84. Okay, if we're gonna find the standard deviation, we have to verify that the 10% condition is met. So in an FRQ situation here, you need to write something like this. You need to show that you have taken into account that 10% condition. So assuming that n equals 100 students is less than 10% of the students in a large high school. So we're gonna assume that 100 is less than 10% of the students in the school. Okay, that there are more than 1,000 students, but you have to write this, that you are verifying that 10% condition. All right, and so then the formula is p 0.84 times 1 minus p divided by n. Okay, so our standard deviation is 0.0367. Okay, and our interpretation sentence is very similar to all of the ones that we've done before. All right. In a simple random sample of 100, the sample proportion in regular use of backpack will typically vary by about 0.0367 from the true proportion of p equals 0.084. There's your interpretation template for those of you that like having that. All right, so then part C, describe the shape of the sampling distribution. All right, that's where we're going to check the large counts conditions. Okay, so our sample size is 100, so 100 times p, 0.84, is equal to 84. That number is bigger than 10. And 100 times 1 minus 0.84 is 16, which is also bigger than 10. So because both of those numbers are greater than or equal to 10, the sampling distribution of p hat is approximately normal. Okay, you have to show this math and say greater than or equal to 10. You cannot just say the large counts condition is satisfied. You have to show it. Okay, and then second example of how we can use those normal probabilities when the large counts condition is met. So we have a simple random example of 1,500 first-year college students, and we ask them how far away their home is. 35% of all first-year students attend college within 50 miles of home. So that's our P, population proportion, 0.35. Find the probability that the random sample will give a result within 2 percentage points of the true value. Okay, so first thing is we know that the mean should be 0.35. Okay, because the mean is equal to the population proportion. Then we, again, we're going to write this sentence every time, assuming that 1,500 is less than 10% of all first-year college students. That's a reasonable assumption. We can use this formula to find the standard deviation. And then we're going to verify our large counts condition, n times p and n times 1 minus p. Both of these numbers are greater than 10, so we can say it's approximately normal, which means I can use my calculator now. And I want to be within 2 percentage points, so I want to be from somewhere between 0.33 and 0.37, because that would give me within 2 percentage points of 35%. The mean we know is 0.35. The standard deviation we calculated 0.0123. And the result that we would get from that calculator there is 0.8961. All right, and that's all for 7.2.